Hello and welcome to my video presentation. My name is Weissmann. I'm from the University of Heidelberg and I'm going to talk about continuous time limits for ensemble Kalman inversion. This is joint work with Dirk Plömka, Claudia Schillings and Philipp Wacker. So in inverse problems, we're interested in the recurring of some unknown quantity theta given from noisy observation y. These measurements for y are indirectly observed through some possibly nonlinear fault map H and perturbed by Gaussian additive noise. In the optimization context, we aim to solve inverse problems by minimizing a regularized loss function. This regularized loss function is on the one side given by some data misfit functional and on the other side by some regularization function. In the Bayesian method, we view the unknown quantity theta and the observation y as random variables. And then the task of inverse problems is, given some prior information Q0 on the unknown quantity theta and the realization of the observation y, we condition the distribution on the unknown quantity on this realization. And then the posterior distribution can be expressed absolutely continuous with respect to this prior information and scaled by the data misfit. The ensemble Kalman filter for inverse problems can be interpreted as a sequential Monte Carlo approximation to the posterior distribution. So we start by this representation of the posterior distribution, and then we go sequentially from the prior information, giving more and more weights to the data. We go sequentially to the posterior distribution. And therefore, we introduce this artificial step size, and we express the time steps in this form. So given the current distribution, we give more and more weight to the data. And the ensemble Kalman filter or the ensemble Kalman inversion is now a particle, or can be interpreted as a particle approximation for the sequential update step. So given a particle system, we define the mean and the sample covariance, and also the mean and the covariance map through this observation forward map. And then the update step can be written as an approximate Gaussian update step. So we have these updates for our particle system where we introduce perturbed observations, which means that given our observation, we perturb them artificially by Gaussian noise for each update step and for each particle system. And in the end, our estimate of the ensemble Kalman inversion is the mean over all particles. Okay, and now we rewrite the update step by splitting the observations and the noise, and then we obtain the following form. And in this form, we can somehow let now h go to zero, and therefore this expression and also this expression should go to zero or should approach zero. And therefore, this whole expression looks very similar to Euler-Maruyama discretization for the coupled system of SDEs below. So in these coupled system of SDEs, we have for each particle an SDE, which is driven by a Brownian motion, which are independent for all particles. And now in this talk, we try to verify this convergence for h going to zero in a rigorous way. And how do we want to do this? So we start with a very general numerical approximation is a result for SDEs in a very general class of functions. Then we are going to apply this to nonlinear ensemble Kalman inversion, where we can verify convergence and probability under very weak assumptions, and we can also verify strong convergence, but here we will need very strong assumptions. And in the linear setting for the forward map, we can also ensure this strong convergence under different assumptions. Okay, how do we start? We start with a general setting. So given a SDE in integral form, given by the drift term and the diffusion term denoted by f and g, we now introduce this numerical approximation where the drift and the diffusions are also approximated of order h. And now the continuous time formulation is just the continuous time interpolation of this discretization scheme. And our aim is to minimize or to bound this error between the SDE solution in integral form and its continuous time interpolation from the numerical discretization scheme. Okay, here we state our assumptions. That's mainly the assumptions between our drift approximation and the true drift, and also for the diffusion term and the true diffusion. And the main strategy, how we want to prove the rigorous convergence, is first we introduce a localization, which just forces the solution of the SDE and also of the discretization scheme to be bounded. And under these localized times, we can prove local convergence for the error. And in the end, we of course need to remove the stopping time to prove the global convergence of the scheme. Okay, and in this setting, we can prove two main results. The first is the convergence in probability. So given that our localized errors converge with a given rate, and also there exists a monotone growing function such that we can bound the localized moments, then we obtain this form of convergence in probability. So the supremum of the error converges to zero as the error tolerance goes to zero as well. So the second main result is this strong convergence result. On the one side, we need that the localized errors converge to zero, and as well the monotone growing function to bound the localized moments again. But additionally, we need now two assumptions. On the one side, we need to bound the moments of the SDE solution, and on the other side, we need to bound the continuous time interpolation of the numerical approximation scheme sufficiently. And under these assumptions, so if we can bound these expressions, we can prove that the supremum of the expected error in LP converges to zero, where LP is bounded by Q and 2. Okay, and how do we want to apply this approach now to ensemble Kalman inversion? So in ensemble Kalman inversion in discrete formulation, we now define FH as this expression and GH as this expression. And over here, we have defined our drift term and the diffusion term with this. So as I said in the beginning, we expect that letting H going to zero, that this expression converges to this expression, and as well for the diffusion term. So this H multiplied by the sample currents should go to zero. So we expect that GH converges to G. And under for these definition of functions, we have verified our assumptions A, which we stated in the beginning. And we can also formulate now the convergence result. So for the nonlinear EKI, convergence in probability can be verified under very weak assumptions. So we mainly need to find this localized moment bound. And here we can define, so this can increase very slowly. So we define a logarithmic, or we prove a logarithmic bound on the particle system by defining this log 1 plus set and proving that this solution of the SDE is bounded. And our second main result for nonlinear ensemble Kalman inversion is the strong convergence. Here, as I said in the beginning, we need a very strong assumption. So we need to assume that the LQ norm of the SDE solution, as well as the LQ norm of the discretization scheme, is bounded by some constant. And then we can prove the strong convergence of the whole method. And now the question, of course, arises, can we prove these bounds, or under which setting we can verify these bounds? And here we come to the linear assumption. So we assume that our forward map is linear, denoted by this L. And under very weak assumptions, or for very general forward maps L, we now can prove that the SDE solution is bounded by some constant. It's left to prove that now the discretization scheme, so the numerical approximation, is bounded as well. And therefore, we can prove under different conditions that this bound is verified. So if we first assume very general linear forward maps, we are able to bound the L1 norm of this numerical approximation scheme. But in this case, our constant is growing with square root of t. So the bound will get worse if t increases. On the other side, we can initialize our particle system in the image space, which means that none of these particles lie in the kernel of our forward map. And then we can prove L2 bounds for our particle system, where this constant is now independent of h and the time. And additionally, including Tikhonov regularization, which basically means that we extend our forward system by the identity map. So we can somehow observe the whole system artificially. And now in this setting, we can also prove the uniform bounds of the L2 norm, where the constant is again independent of h and also of the time t. With this, let me summarize the presentation. So we have derived two numerical approximation results for a very general class of SDEs. We formulated the abstract convergence result on a weak assumption for ensemble-Kalman inversion, and we have verified the strong convergence in various settings for linear ensemble-Kalman inversion. And now, of course, the ongoing work is extending these results to a strong convergence result in a nonlinear setting. So the forward map of the inverse problem is nonlinear. We aim to prove higher moments in the linear setting. As well, we want to consider the long-time behavior of the derived approximation results. And yeah, let me mention our preprint. It's on arXiv, entitled with Continuous Time Limit of Stochastic Ensemble-Kalman Inversion, Strong Convergence Analysis. Thank you for your attention.